Okay, I think we can start. I'm Krzysztof. I'll talk about dependent types. I'll be using Agda as a language to show this. However, I don't treat this as an Agda tutorial, more like of a dependent types tutorial. Most concepts will transfer to other dependently typed languages. Agda and Idris are the two commonly used languages that most resemble Haskell syntax, so they are a natural choice here. There is also Coq, but Coq resembles more ML syntax. If you think of Haskell, Haskell is often seen as some bleeding edge language. Which gets many different type system extensions, is like a laboratory for type system extensions, and some things in Haskell later land in mainstream languages, like more mainstream languages. And you can think of dependent types as something more Haskell than Haskell, and dependent types are going to land in Haskell sooner or later because there is an ongoing work to do this. And they are pretty interesting. I've learned a lot. They changed your way of looking at types, and I think this is a pretty good thing. Agda is more of a proof assistant than a programming language. However, you can also use it as a programming language. Idris is more of a programming language than a proof assistant. However, I won't be doing many proofs here. I will be just illustrating the concepts. One issue is that when you use a dependently typed language, programming more resembles a dialogue with the type checker, even more than in Haskell's case. So you need a good editor integration, and the one that is built into Agda is using Emacs. I don't like Emacs. I'm a long-time Vim user, and I avoided Agda for some time. However, then I saw this. Agda is such a great language, I'm prepared to overcome my hatred of Emacs to use it. And I thought, wow, Agda must be a pretty good language. So yes, so you can get over your hatred of Emacs and install Agda and use it. So this is the font size good enough? So this is a very simple module. I will not be doing imports, so we'll be more of creating a universe from scratch thing here. So this is a Boolean type, and the Haskell equivalent is data bool equals false or true. So you can list constructors, several constructors separated by a space. The typing is indicated by a single colon, unlike double colon in Haskell. Set is the kind of bool. So any simple type like bool has the kind set, which corresponds to asterisk in Haskell, or type in Haskell if you import data kind. Notice that I used false and true are lowercase, but in Haskell all type constructors have to be uppercase. Agda doesn't enforce distinction between lowercase, uppercase, or even most symbols. So if I wanted to, I could call this way, and this would still be a single token that can be used whenever you would say true. What is extremely important is spaces. Spaces separate tokens, and for example, if I don't do this, then Agda will think the true value is called true colon. So colon is a typing judgment only if it's separated by spaces. But it can be a part of a name. Okay. So let's write our first function. So this is the representation of natural numbers. This is 0 and successor. So this is a pretty inefficient implementation of natural numbers. If you want to say 3, you say suck of 0. And let's write an addition function for this. Add nat to nat to nat, and we'll have two parameters. I will now put a hole, which is indicated by a question mark. This means I don't know this yet. By default, you don't have syntax highlighting unless you load the file. Syntax highlighting is not provided by editor, but rather by Agda. So I load the file.
Is question mark like undefined?
Kind of. It's a whole. The point is that in Haskell, undefined is a proper value. Well, it is kind of a value. You can use it in an expression. In Agda, a whole actually indicates that something is missing, and there is a built-in support for this. Support for this. So it's like undefined, but the language knows about this. So I put this whole, and after I load this file, you see this green 0. This indicates a whole, and on the bottom you see all goals. All goals means that you have a program, but there is still something to be filled. So you can, in a sense, you can compile an incomplete program. And after you fill all goals, you will see that all done. So to add two numbers, well, you need to case split on x. So let me do this. I type x, and I tell Agda to case split. So I now see that I now get two cases, and my one whole was now changed into two wholes. So instead of one problem, I now have two problems. But this is easy to fill. I can also ask Agda about context, and I'm not sure if you see this well, but the goal is not. This is like what I'd like to fill in the whole, and below this line, you see that y is a not. So I get information about the environment, about the context. So to add 0 is y. I can now fill the whole, and when I fill the whole, Agda also type checks. So you cannot, if you try to write something that won't type check, Agda won't allow you. Let's see here. For example, if I try to type just oops, if I try just suck, and I say whole, and I try to fill it, I see an error. Okay, so this will be a successor of something. I can put a whole inside a whole. So this is like when I do a partial program refinement, or I couldn't even put multiple wholes. So let me fill it this way. And now I need to type here a natural number, while I have y and x, and this is at xy. What's also nice is that when I ask Agda to fill this whole, the parentheses are automatically added. So this resembles more of, I feel more like I'm programming with an abstract syntax tree than just with a text. So this is nice. Okay, let's now try to use this. Add suck 0, suck 0. So this is 1 plus 2, and we got the result is 3. Now this is a bit ugly, so there is a special built-in directive to say I would like to use the normal Arabic decimals. Built-in natural nat. And once I have this, I can now say add 4, 5, and I see 9. Here. Okay.
So what does built-in natural nat do?
What's gone?
What does built-in natural nat do?
Oh, it allows me to use the normal number syntax. Previously, I had to type add 0, suck 0, and here I can use. So Agda knows, for example, that so this line.
What if you said built-in natural bool?
Allows me to write 3 instead of suck.
So what if you did built-in natural bool?
You will get an error because Agda enforces that that it has the proper structure.
Is this just a syntax simplification, or is it optimized?
That's a good question. Naturals are optimized, and now you can use 1 million. Previously, this might be slow. The problem, however, is now this add function is not optimized. So while storing a single number is easy, this add function will be slow. So if I try to add 10 and 20, yes, that's 30. But if I try to add 1, yep, I don't see the result. And if I try now to add 1 and 2, I see another command is currently in progress. And I will kill Agda. Okay. And there is a way to get around this as well. The library gives you a more efficient representation of numbers, but this is not really that interesting, I would say. So I'll skip over this. If you are trying to fill a hole, and you see this message, text is read only, then turn off overwrite mode. Sorry. Okay. Okay. Now this add function, it would be nice if we would be able to use it as an operator. Agda has operators, and they are more powerful than in Haskell. In Haskell, operators are binary, but in Agda you can have operators of any fixity. And to do this, you indicate the places where the operand goes using underscore. So I'll replace add by underscore plus underscore. And once I have this, I can now type 2 plus 3 and I get 5. And I can also write this in a more natural way. X plus y. Okay. So let's now write.
This means that underscore cannot be in the name.
That's correct. Underscore. So what you can do, well, kind of. Underscore can divide a name into parts. However, you still have this name in scope, underscore plus underscore. So it doesn't have to be a function. I could write underscore x underscore is not, which is equal to 2, and I can now evaluate underscore x2. Okay, so using underscores in names means that you get the operator syntax, but you can still use the name as is. Okay, so let's write now an even simpler function, identity, and I will write two identities. One is identity on booleans, and the other will be identity on natural numbers. And you see here that we'd like to have a single identity function, but now we have two. So we have repetition in code. We have two functions that are defined in the same way. So how to get rid of this repetition? Well, I'd like to show something similar. So the problem is that while the definitions are the same, the type signatures are different. Well, but what happens if you have two functions that have different definitions? For example, we have one function xy, which is foo x for y plus bar x, and you have another function that is similar, but it has the number 10 here. Well, in this case, the solution is, as you know, to define another function which takes an extra parameter. And then we can represent the previous two functions as special cases. This will be f4, and this will be f10. Okay, so this is abstraction. You have some repeated code, some repetition in your code, and you can extract the repetition to a function. And after this, your function takes one more argument. Okay. Now in Haskell, you do that only for values, but in dependently typed programming languages, values and types are very similar to each other. Types are first-class values, and what you can do is you can make this parameter, which is repeated here, here and here, to be you can make this type, which occurs in the signature, also a parameter. And to do this, you can say ID, A is a set, and now I have a set as my parameter, and I can say A to A. I ignore this set, which is given to me as a parameter, and I can say ID underscore x equals x. And this compiles, and I can use this ID not 4, and I get 4. Notice that this function has one more argument than those two. I can, in fact, define those two in using ID. So this will be ID bool. This will be ID not. So notice we have something that you don't normally see in Haskell, passing types, having types and values mixed in a single expression. Now, if you think about the Haskell way of doing things, we have, for example, an ID function, and this seems to be different because you don't have any parameter. This ID function just takes an A and returns an A. However, Haskell in fact works pretty similarly to what Agda is doing under the hood. And you can say print explicit for alls, and you will see this for all. So this is where this A is bound, and in fact this ID takes a type parameter. For example, I can, just like ID has type bool, I can say ID at bool, and this function now has the is just from bool to bool. Seeing this, I would say is pretty useful if you'd like to look at Haskell more deeply, and it explains some phenomena. For example, some people freak out when they see let x equals read 0. So now you have this x which is equal to read 0, and if I cast x, like give a type signature to x, it's an int, it's a 0. If I say it's a float, it's 0.0, and if I say it's a unit, I get an exception. So this looks pretty weird. I have some weird value that changes depending on what type I give. However, what is really happening is that this read function has a type argument, and we haven't specified it here, and giving this type signature actually causes the implicit type argument to be given. So I can in fact say read at int 0 or read at float 0. So there is no magic, it's just there is an implicit type parameter that you wouldn't normally see. Another example is that you've seen this for all can be explicitly shown, and this means that you don't have to start a type with for all. You can do things like I have a function that takes for all a list a to int, and I can say something like oops. To int. So this is a function which takes a polymorphic function. So I cannot pass to f say summing, because while summing works on a list of a, it only works on a list of integers, but I can pass the function length, and in this case it will compute length of a 2-element list plus length of a 1-element list. Finally, one more example of this phenomenon is that sometimes when you write a recursive function in Haskell, you have to add a type signature. Simply, the compiler will not allow you to compile without a type signature. And this is because of polymorphic recursion. It means that the type parameter might also change between recursive calls. Okay. In Agda,
Isn't it because like type inference would become undecidable function?
this is correct. So in Haskell you have to call the type parameter that cannot change in recursive calls unless you give an explicit type signature, because it's easier to check a given type than to infer it. Okay, in Agda, you need to specify explicitly this a, meaning if I just say this, Agda will complain about a not being defined, unlike Haskell. However, you don't have to specify this argument every time you call ID. One option is to use underscore, which means please infer this argument. So I can say ID underscore 3, and Agda has inferred that that underscore should be not. Another option is you can use an implicit argument. Instead of normal parentheses, you can use the curly ones. This means ID takes this value a. However, in any context, this value a should be inferred by default. So it's like you, in every place where you use ID, you are passing the underscore, and Agda will complain if it cannot infer this a. you can also override this and pass implicit A explicitly this way. Okay, and in Haskell, generally values are explicit and types are implicit, but in Agda this distinction is no longer the same. And if I really wanted to, I could make ID give an implicit argument here. Well, if I want to do this, then I also need to bind A. Yep. So I would have now to say this. Okay.
Right now X is implicit.
That's correct.
What
So
does that mean? What does that mean?
it means that whenever you call ID, you don't supply X by default. Agda will try to infer it.
How does that work?
Hmm?
Can you show an example?
Sure. Just using the underscore itself is this case. So ID behaves the same way.
What does it infer it as?
Well, it can infer based on type information, and there will be examples later. But so you can think of ID. ID currently behaves like an underscore. You have seen that Agda can infer some missing parts in an expression.
Yeah, but X is a value here, not a type, right?
Well, we have first class types, which means the distinction between values and types is not so clear.
Okay, but the type can be inferred based on this X, right? And how do we infer the X based on what?
I will give examples of this later. Okay. Okay. I was talking about this how I'm doing on time. 24. Okay. I was doing about this plus operator, and let's write an if then else. So if then else is not a built-in syntax, and I can write it bool to A to A to A. Then T else F equals question mark. Sorry, that should be set. So I case split on B, and if it's false, I return F. If it's true, I return T. Simple enough. So I can now use if then else as an operator. If true, then 42 as 0. I can if then else is polymorphic, so I can use it on any type. Whoops. And okay, let me now write another function. I will call it magic. Magic will take a boolean and will return if B, then not, else bool. Magic for true will be 10. Magic for false will be, say, true. Oh, and I need to enable one option. I will actually, you can just ignore it. This function is a bit weird.
Set lives in set.
Hmm?
So set lives in set.
Yes.
Set colon set.
Yes. So this function looks a bit weird. You might think it's dynamic typing, that a function sometimes returns a value of type 10 and sometimes returns a value of type true, but it's not dynamic typing. For example, if I change false and true, it won't load. I'd like to flip this idea around. This is not dynamic typing, but whenever you see dynamic typing, a situation where it seems that you really need to have a dynamic type, think about this example. Perhaps the code that you are doing, that is doing some dynamic stuff, could be written using dependent types, and then you would have these static guarantees. So the situations I'm thinking of is when the schema of the data you are processing is not fixed. It has to be loaded from a file, for example. and you don't know during compile time what will be the exact shape. So this is one area where static types come into play. Another thing to notice is that to type check this function, Agda had to run if then else. If I change the definition of if then else to always return false, this doesn't compile. Which means execution of programs and type checking is no longer two separate things. They are intertwined.
Why would it not compile?
It does complain, right? So
why would it, why would that happen? It could return always false. What is wrong with that?
so it doesn't compile.
Okay, because we have 10 over there.
Because this if now becomes always a bool, and this is not a bool. Okay.
So how are you able to still do type checking like statically? How are you still able to do type checking statically?
Statically, it doesn't mean that you cannot evaluate parts of a program, right? Statically means, well, what does it mean? You do it compile time, right? Evaluation. So one consequence is that if you'd like to have dependent types, generally you will do this in a language which is pure, because if your functions are not pure, you would have random I/O effects happening during compilation. Okay.
Does it happen that there are recursive calls between?
Oh, that's a good question. So Agda actually enforces totality, and a function can be non-total. One way is that you forgot a case. If I forgot a case, you get an error, incomplete pattern matching. And I would say this is a bit weird that in Haskell this is also not an error. I think an incomplete pattern match should be an error, and you would have to explicitly differ it. Or another thing is that what happens when your recursion doesn't stop. So let's say instead of this x, I will type suck x, and you got an error. Termination checking failed, and Agda refuses to compile. Now you can disable termination checking, and in this case you are not guaranteed that compilation of your program will halt. Agda, I think, might refuse to evaluate terms which are not guaranteed to halt, but I think it might depend on something.
It restricts itself to primitive recursive functions.
So Agda forces you to write functions so that they obviously terminate. And you might think of halting problem and so on, but in fact, any sensible real-world program is guaranteed to halt, like a function like this. Well, it is true that checking whether a general function halts is undecidable, but you don't want just to be mechanically decided. You want, for example, a human to be able to see, hey, this function terminates, and you want like things to pass code review, for example. So it's good if a function obviously terminates, and Agda enforces this.
So does it restrict itself to primitive recursion or something?
By default, you need to use smaller arguments. So you can think of primitive recursion, but it's not like primitive recursion, primitive recursive functions. You can write things like Ackermann function. However, there are some extensions you can use to indicate size when recursion is non-trivial.
Does the disabling of the totality checking speed up the compilation speed a lot or not at all?
I have no idea.
No, okay.
I wouldn't expect this because totality checking is just like based on syntax.
Oh, okay.
While actually running functions like this might take more time. And in fact, whoops, sorry. Agda documentation actually encourages people to split modules into several smaller ones because this might speed up compilation. Okay. What else do I have here? Oh, another thing is that in Haskell you have something called substitution property. Substitution means that if I have a program and it has a value of some type somewhere, an expression, and I replace this expression by something that has the same type, the program will still type check. Okay, I have a configuration variable that's false. I replace it by true, the program will still type check. It might behave differently, but it will still type check. This is not the case here. And to see this, well, I define as a set, which is, sorry, not a set. I'll define a natural number, which will be equal to magic true. And yes, this type checks, but if I change this to magic false, it won't. Okay? So you lose this substitution property. Okay, that's all when it comes to magic. Let's now write the dollar operator, and there are no surprises here. Okay. Oh, I need to fix the add function I broke earlier. Okay. So this is the dollar operator. You can use it in a way similar to what you do in Haskell. The problem, however, is that this dollar operator, while you can use it, for example, on add, well, on plus for $2 to get 6, I cannot use it on magic because of some error. The issue is that this operator is working only on non-dependent functions, on functions where the domain does, where the result, the type of the result does not depend on the value that is given on the input. So this is a non-dependent function, but this is a dependent function.
So the right hand side of the colon in the magic, that is not of kind set.
This is of kind set. This
no,
is a set.
Is this of kind set?
Yes, this is a set.
So why is it not working again?
Because this is not the problem. Yes, A is a set, but there is a dependency between A and B that is not visible.
Okay.
So if you do this, well, A would have to be bool, but what would be B? Right? B here has to be a fixed set in this definition, but in fact what we have here is that B is not a fixed set, it's something that depends on B. So we need to make this dependency explicit, and I will define a new dependent application operator. A is a set, and B this time, well, before I say what will be B, what will be on the right hand side? We will take A, which is an A, and return a BA. Okay? So this A works similarly to this B. So this is the type parameter, that the parameter that is the input value, and now the domain is now allowed to depend on A. And do you know what should be the type of B? A to set. Okay. Yeah, I call this operator a bit funnily because it's a mix of both letters and symbols. And this type checks. In fact, the previous operator is a special case of this one, so I could write it this way, except Agda enforces that you write your definitions top to bottom. So what I can do is I can move the entire definition down, or I can just take the type signature and move it here, and this also works. So this is how you can get mutual recursive functions. If your mutual recursion is also on the type level, then there is also a declaration for this. And seeing this, we don't really need $. We can make our normal $, to be the dependently typed version. Okay. So now we have seen, for example, that the $function generalizes to dependent types. And you might wonder what other combinators on functions generalize and which do not. For example, flip. Well, if you have a function like a to ba to c, the problem is that you cannot flip this because you have to supply the first argument first to know its value so that you will be able to type check the second argument. Okay? Like there is no way, for example, to if this function was written this way, then this a is not defined, and let's say if you try to partially apply this function, the type wouldn't be clear. But what you can do, for example, is write a limited flip. Let's write this one. So we have a, which is a set, b is from a to set, and c, d are sets. And let's say this goes to c to a b a d, and flip f c a b equals f a b c. So generally the rule is if we have an expression like this, a to a, b a, c d, then I can have the arguments a, b, c in any order as long as b is after a. What about mapping? Well, if you have a list like false and true, and you try to map magic function over it, then you would be getting true and 10, right? So you would start with a homogeneous list, and you would end up with a list that's false and that's true and 10. And the conclusion here is that there is no dependently typed map on homogeneous lists, because it would have to return a heterogeneous list. Okay, if you'd like a rather hard challenge, try writing dependent composition. It is rather difficult because you have a, b, c, and b might depend on a, while c might depend both on b and a. So even writing the type will be pretty tricky. Like the implementation is the same as in the non-dependently typed version. Okay, what's with the time?
What about, for example, in this example of composite functions? Can't we just write the definition and ask for the type?
No. In general, type inference is undecidable. So you could, for example, infer a non-dependently version. Well, let me even try it. Compose fgx f of gx. Yeah, you are getting something good. Okay. Let me check how I covered everything. I think I did. Okay. Data types. Let's write.
Could we define flip in a regular way, assuming that there is no dependency?
Right.
This could be done, right?
Yes, the normal. You can just take the normal Haskell version and copy paste it, and it works the same way. Like flip to a b.
Assuming there is no.
Yes.
Yeah,
so this. If you write it this way, it means there is no dependency. If you would like to say that there is a dependency, you need to name the parameter and use it here. But this version, wait, you see, flip to f ba equals f a b. Type checks normally. It's just you can use it only on a non-dependent function. Okay. Data types. Well, remember I wrote those two data types. I will now write a data type that you hopefully all know. Data either. Left goes to either a, b. Okay. The Haskell version is, I enter data either AB equals left A or right B. Okay. Some things to note. This is how you give parameters to a type. This means that, that in the definition of either, this A and B will be in scope here and here. If you so let's write a value. Either value.
After data AB set, we also put another set. Is that necessary?
Yeah, I would like to get to this later. You can, for now, you can just put them on the left. And this means they scope uniformly over everything. Either value, well, let's say that it will be either not bool equals, say, right bool. Okay, this, sorry, not right bool, right true. Okay, this type checks and this type checks. So no surprises here. Now, if you think about how this value is stored in memory, then you need to remember whether it's left or right in one part of memory, and in another part of memory you will have a representation of either A or B. Okay, so it's a tagged union. There is a part which specifies whether it is an A or B, and there is another field which has whose value is either A or B depending on the first on the tag. Well, this might resemble that magic function from earlier. There is a tag, and sometimes it's a natural number, and sometimes it's a Boolean. And in fact, you can define a different either, but it will be like either differently, either two, where I will still have A and B, which are a set, but there will be just one constructor, not two, that will handle both cases, and I will call it both. That will take a Boolean, that will take if B, then A as B, and it will return either to AB. Okay, so this type and this type can be exchanged for each other. And let's write conversion functions. Convert one, either AB to either to AB. Convert one x equals question mark. Oh, sorry. Set. Okay. So my goal is to write either to AB while I have either AB. I can case split on x. Now on this side my goal is either to AB, and I have just an A. So the solution is both true x. I need to put true here and this way, and here this will be both false x, right? I actually told Agda to infer this for me. So you have some limited way of guiding the way you write programs using types. I didn't write those things myself, and I would say this is the more important part. When you write Haskell, people often give advertisements that Haskell is great because yes, it has static types, but like in a dynamic language, you don't need to write those types. Well, I think this is kind of true, but the power of types, I would say, is the other direction. You have a type, and it can guide the program writing. It can guide what value you will write. So you might think of that you first give a general shape of your program. You define types, and once you have types, it will be easier to write your program using features like case splitting. Then if you start with values and then try inferring the type, that might work or might end up not doing what you want in the end. Okay, we have convert 1. Let's now write convert 2. Either to AB to either AB. Question mark. So again, I can case split on x. I get now both bx. and I can case split on P, and this will be right x and left x. Hopefully no surprises here. Now if you think about this either two, if we had a data type that had, instead of booleans, we had like 3 constructors, then you could model a 3-way either, right? So instead of an if statement, we could have like a case statement essentially. But there is in fact nothing stopping us from having any general type as the first argument. It doesn't have to be a bool, it doesn't have to be an enumeration type, it can be anything, and the second part of the tuple will be the type of the second part of the tuple will be dependent on the value of the first one. Just like here, except we are not enforcing the first part to have to be just a boolean. Okay, and this is called a pair. So a pair takes a set, like with dependent functions. The second argument is a function that takes the value here, of this type, and we have a pair. The first argument will be an A, the second argument will be a B of A. As a result, we got a set. Whoops. Sorry, we got a pair AB. Okay. So this is a generalization of the previous case. And let's write a conversion function. Okay. We have a set. Let's say we have AB set, and let's convert from either to AB to pair. And what should I write here? Well, the first component, well, we'd like to write this type as a special case of this type.
So it's pair bool.
So A will be a boolean,
And it's if
and BA should be this function, right?
so you go P colon U.
So now we need so BA. So we now need a function that when it's true is equal to A, and when it's false it's equal to B. How do you write a function?
You have to name the bool.
You use a lambda. Okay, we have a lambda, but notice that unlike in Haskell where you put lambdas only in values, here we put a lambda after a type signature. If B, then A.
Couldn't you write B colon bool and do that?
No, like there is no syntax for this. Now you can define this syntax if you want. Convert tree of something will be question mark. Okay, so I am given an either 2AB, and I need to return a pair of this type. Okay, let's case split on X. Well, there is just one case. 30 seconds. This will be just per bx, right? We are changing this constructor to this constructor. Okay, I think this is a good moment to take a break. Okay, let's continue. So I finished at this pair type, which is a dependent pair, and we have shown that this pair type generalizes this either two for the case when the first component is just a boolean and the second component is an if function, similar to that merging function. I'd like to make one small cosmetic change. Notice this pair constructor. I will write it this way. Okay. So that's a comma, and you can use comma just like a normal operator or a constructor. Let's write, so since we have a pair, this is a generalization of a normal tuple, just like the ones you see in Haskell, where not Python. Just like this tuple, it has the type number and character. This is a non-dependent tuple. This is a generalization where the first component might depend on the where the second component might depend on the first component. Let's write FST and SND. So let's start with first. This will be pair AB to A B set. So xy equals x. B set, B is A to set. Okay. What about second? Well, implementing second is easy, but what will be its type? Well, surely it will take a pair AB.
B?
Well, you cannot put a B because B is not a set. B is a function from A to set.
So lambda
Hmm?
A to set? So lambda A B of A.
Well, a lambda won't be then a set. It will be a function, right? To obtain, well, clearly we need something with B here. It cannot be just B. Well, let's try it on an example. Let's suppose I have that either pair, and it's and you know it's either false and a number, or true, and then it's a boolean. Okay. So the first projection is simple because it's always a boolean. But the second projection depends. Okay. So either would be this this specific case. But here we have a general function B. So we need to apply to B something, okay? And what should this be?
Apply with A.
Well, if I type BA, then A is a set, and we don't want to apply the set A.
So it's B small a, where small
We
a
want to apply the value A, which was the first component of the tuple.
So you write a colon a in the pair signature.
This means the type of this value will depend on the pair. Okay? So I will call this P, and what will this be? FST of P. Okay? And that touches. Okay? So there is a big difference between non-dependent tuples that you have in Haskell and those tuples. They are not symmetric. Just like when you have a dependent function with multiple parameters, the order matters and you cannot always flip those. Here you cannot, there is no general swap function on those pairs, because the second component, to know its type, you need to know the value of the first component. So there is no swap. Of course, if you write let's write a product AB set, where
So this was the sigma
This is a sigma type, yes, I will explain this. Product AB. So this is a non-dependent tuple. I can use it this way. Product not bool x equals 42, comma false. Have you noticed something weird? Comma is overloaded. Agda is smart enough to allow you to overload constructors. So I can use comma both to create a dependent pair and to create a non-dependent pair. So the names of the constructors can clash. You can disambiguate if this is necessary, but generally you can use the same names of constructors in multiple places because types can tell you what is the desired constructor.
Can you use comma in non-infix position at the beginning?
Well, I can name a function comma. Well, I can do this, for example. I cannot name a function this way because that would be a conflict. You can have multiple type constructors with the same name, but you cannot have multiple functions with the same name. But for example, I can write, I can call this x actually this way, for example, and that works. So in
I mean, can you use this existing comma constructor in non-infix position?
Well, I can do this.
Oh, in this way.
Right? So if a variable name has underscores, you can still use it if you give it the full name. The operator syntax allows you to apply it if you replace every underscore with an expression. Okay. So we now have dependent pairs, and dependent pairs are known as sigma types. Sigma type, while dependent functions, which you have seen as those, are known as pi type. Okay, and I will now explain why is this the case. If you think about, let's create another data type. I will call it weekday. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Okay, we have weekday, and this weekday type has 7 elements. So how many are there elements of type product bool weekday? There are 14, right? I can have, for example, Monday false, false Monday. Okay. Now, if you think about those 14 values, you can arrange them in a table that will look like this. I have those 7 days. I will replace this by false. Okay, I won't try to do this automatically. Tuesday. So those are the 7 values where the first component is false, and those are the pairs where the second component is true. Okay. So this is a non-dependent tuple, and this corresponds to a nice table. You have 2 rows and 7 columns. However, when you have a dependent pair, this will no longer be a nice rectangle, because it might turn out that the first row has 3 elements and the second row has 4 elements. Right? When we have something like either bool weekday, the first will be left true, right, left true, left false, and the second row will be right Monday, right Tuesday, and so on. So this will no longer be a rectangular array, it will be jagged. Now, if you'd like to compute the number here, it's just multiplication, so 7 times 2. If you'd like to compute how many are there elements in this type, well, you need to add up. If you number the rows, this will be f1 plus f2 plus fn. Okay, you are just adding the number of rows in this jagged array, and this is why it's known sigma, because sigma is the notation for addition. You are changing a general rectangle to a jagged array.
Also because this is kind of a generalization of some types, right?
Yes. When it comes to the product, well, how many are there functions of type bool to weekday? There are 49, because such a function is like two different values, right? You need to specify what is its output on false value and what is the output on the true value. So it's 7 times 7, okay? But if it's a dependent function, those two, so this is the possible values for true and possible values for false. But if it's a dependent function,
but how does that work? I mean, does it even work like that? Because if you put in true and you only have one value, how are you going to know if it's Wednesday, Tuesday, or Monday? It's going to be one of those, right?
I mean, if you the number of different functions, right? So,
okay.
So like fun true Monday, fun false Tuesday. This is one of 49 different combinations you can write. Okay, you have 7 options here and 7 options here. So it's.
You would be able to write fun true Wednesday, and that would go bad.
In this type, yes, it's from Boolean to a weekday.
But not together with this one, right? I mean, then you have like fun true with either Monday or Wednesday, and you don't know which one it is.
So
like if you write one more line here, and you write fun true Wednesday.
Well, that won't compile because you like this will be like this is a dead case, right?
Right. Okay.
So it's like this is the same function. A function is defined on the values, right?
Yeah. Okay.
So we have 7 times 7. And those 7s are the number of possible values for true. This is possible number of values for false. However, when you have a dependent function, so not like one, but one where you have this b bool, and there is if b then weekday as something as, let's say, bool, well, it won't be 7 times 7, it will be 7 times 2. And I hope that in general you see that it's f1 times f2 times something times fn, which is equal to pi. That's the notation pi f, and this is sigma f. So that's the notation for generalized product. Just like you had that geometrical view where you changed a rectangle to a jagged array, here you can think that a normal function is an n-dimensional cube, and you are changing it to a cuboid, like a cube, but every side has its own length. So it could be like something like this, this, and this. Okay. I have an image. Okay. Here is another point. Suppose I have a pair, and this pair is equal to true and 42. Okay, a dependent pair. What will be its type? Surely it is pair of a Boolean, but now, well, it could be a pair of a Boolean, and the second component would always be a natural number, or it could be a function here where you have if b then natural numbers as something else, and there is no way to tell. Okay, which means in general there is no type inference. So Agda in fact enforces in most cases that you place a function, a signature because there is no general way to tell. So signatures are used to guide disambiguation, as in this case, but they are also essential because in general you cannot infer the type. Yes, you could do tricks like give this constructor and supply an implicit argument, but if you do that, you might as well annotate the whole program in the signature, right?
Can it be polymorphic on this second argument?
Once again?
Can't it be polymorphic on this something else? Can't it be
Well,
a type variable?
Well, yes, it could even be something like this, right? You could have an implicit A here, and yes, if I just say pair equals true 42, there is no way to tell because binding of an implicit argument is not visible. Yes, I can write this, and this actually type checks. Okay, here is another case. I will call this type dynamic. And in Haskell, if you'd like to specify a type synonym, you use the type keyword. You say type t equals integer. In Agda, you don't do that because declarations of types and of values are of the same category. So I will now define a type synonym, dynamic. And my dynamic type will be a pair. And on the first component, it will contain as type. And the second component, depending on the type, I must now specify what will be on the second component, and that will be the type itself. So let me write one value of this dynamic type, dynamic pair. The first argument, the first part of the tuple will be a nut, and the second part will be 42. This works. But if I try to change this to bool, it doesn't. I need to write bool false. Okay? So this is like a sum of all possible types, except it's annotated with the type on the first coordinate. Unfortunately, Agda doesn't allow you to pattern match on set, so you won't learn much from this. What you would have to do is you would need to encode this type in a different way. And one way to do this is use a construction called codes. Code. And let's say I will have just two codes, nut and bool. And I will redefine my dynamic type to contain a pair of code. And I need a function here, interpret, that will interpret a code and will give a set. Notice, if you think in terms of Haskell, this is a value and this is a type, right? So interpret of nut will be nut, interpret of bool will be bool. And now I can change this bool to lowercase bool, and this works. So that
isn't ugly because it kind of introduces the distinction between types and values. This is kind of an
once again. So
I mean, it seems kind of ugly, right? Because you introduce some funny values, some dummy values, to some dummy stuff to.
yeah, there are. If we had pattern matching on set, for example, you wouldn't need this. And in a similar fashion, typeable in Haskell is kind of this way because you are duplicating values. The advantage of this construct is that you can limit the possible things you have on the left in this pair. This pair can now contain only natural numbers or booleans and nothing else.
Is there a reason that we can't pattern match on sets?
Are they erased?
Yes. However, you shouldn't think, you can in fact specify whether an argument is irrelevant, meaning it's erased. And in Agda, this doesn't have to be a type and a value. You can have like a marker that is type and on runtime, and you can have a value that is erased. And Agda enforces that a non-erased value cannot depend on an erased value. erasure irrelevance, meaning if you compile a Haskell program like ID3, I've said that you are passing a type, right? But there is no notion of types during the runtime. So the program that you get after compilation does not contain types. This is type erasure.
Okay. So what is the situation in Agda?
So depends how you, what backend you use to compile Agda. But you can specify irrelevance using a dot, I think. Okay. So let's do some operation and on codes, and let's also add pairs. So pair will be a code to code to code. Now after I have added this constructor Agda complaints, so I need to say interpret code xy equals, and will this be x comma y? It will not be x comma y, because this is a tuple, and instead I need a set. Okay, I didn't explain this. Oh, that shouldn't be code, that should be pair. Print x. Okay. What I'd like to draw your attention is that we have a different name for the constructor here, product, and for the constructor of a value. So this is the type of tuples, while this is an actual tuple. In Haskell, the syntax is the same. Okay, 2, 3, but the type of this tuple is different from this notion of a tuple, because this is a tuple type, and this is a real tuple. Okay? So if you'd like to indicate a real tuple in Haskell on the type level, you need to do it this way. That's a tuple. That's a tuple, and that's a tuple type. Oh, sorry. Okay. Let's try carrying. Where is the non-dependent version of carrying? I'm sorry, I've lost track. We were on this pair. So this is a dynamic, and we can also now have a pair of booleans and nuts, and this pair will be true, 10, and this type checks. Okay, so we now have some arithmetic on types. This interpret function is used to is run on this pair bool nut to determine what will be the type required on the second coordinate. Okay, and in fact you can push this idea further, and this hints at some duality between dependent functions and dependent pairs between sigma and pi. Let's suppose you have a client and a server, and there is a protocol between them, that the client will send 2 numbers to the server, and the server will respond by adding those 2 numbers and sending this to the client. The client might then do something else. So the way you can model this is that, let's say the client will have the number 2, and then we'll have the number 3, and then we'll have a lambda x, and let's say the client will finish by saying x plus 10, and the server will first take an x, then let's take an a, then we'll take a b, and then it will give a plus b, and let's say it will finish with 40. Okay, so the type of the client is a pair which has a number 2 here, and then there is the rest of the protocol, while the server has a function that dictates what will be done next. Okay, so the idea here is that one party has a tuple, while the other party has a function, and you can match those two, and they can interleave. So a client can first give two numbers to the server, and then the server can return another value which will be given to the client. So this is some hint how you can do this type arithmetic to obtain some type-safe protocols where it's clear who is the one who's talking and who's the one who's receiving.
But the client here is this type or value actually?
Sorry. Yes, that should be an equals, not a. Okay. And you can model this by writing something similar to code. So that will be a protocol value, and the protocol will specify who is the one who is talking, and then the client, once you have this protocol value, this will be the type for client, and this will be the type for server. Another thing to notice is that there are no dependent functions here. However, this protocol has a disadvantage in that it always does this thing the same way. Okay, the client is always the first one to talk, then the client, then the server, and so on. If you have dependent types, you can make the next action that will happen depend on the previous one. Okay. So let's write a protocol function, and I will write only the non-dependent version, and I will leave as a homework to write the dependent version. So let's say we have A get not and B get not. So a protocol can finish, or it can get a natural number, and then you need a next action. Okay, and what will be the A action? Let's say A action given a protocol, this will be a set, and A action, let's say that every protocol finishes with a natural number. So if A needs a natural number, it will be it gets a natural number, so you get a nat, and we recursively, sorry, I should actually, okay.
So why is that protocol to protocol shouldn't it be NAT to protocol? A get NAT and B get NAT?
Because it specifies what will be the continuation, what happens afterwards.
Okay.
So let me case split on X. If we finish, then let's say that you specify the natural number as what you have done at the end. If for A, you take the natural number and you continue, and for B, you do this. Okay. For B, the rows are reversed. So this will be product not, and this will be okay. Oh, and this should be action. Okay. So let's now write. Let's now try to run this protocol. To run Unita Protocol, which is P, you need the description of A actions. You need the description of B action, and let's say you get two natural numbers after both finish. So to run this, question mark, and I would say AP. So let's case split on the protocol. If it's finished, our goal is to give the return values of both client and server, and we can do this by just saying A, B. If A gets a natural number, let's see, B is a tuple, so this is the number we'd like to pass from B to A. So I can case split on B. Agda, as you see, uses Unicode, and I try to avoid Unicode in most of the talk, so I'll just rename it to Y. Okay, so my goal is to give, I need to run the protocol further. Run. Okay, so we'll be running P. And now I need the continuation for this. Well, for B it's simple because you just need because we know what's the next action, which is Y. And for P it will be XA. Sorry, AX. Okay. So here is where I am giving the value which was held in this tuple to this function. And let's do something similar here. Okay, split. Run P A B Y. Yeah. So we now have the run function, and let's write a simple protocol. So the protocol will be A gets a natural number, A gets a natural number, B gets a natural number, and they finish. Okay, so that's the protocol. And now let's write A for this protocol. So what should this be? This should be a function. So this will be the server, which will take X and Y, and the server will respond by giving the sum of the two numbers, and it will end with 0. Okay. While the B action will be let's say that it will start with 10, and that it will give 30, and then it will receive the output from the server. Let's call it Z, and it will return Z plus 2. Okay, so I now have defined a protocol and two actions that can be that correspond to both sides of the protocol, and I can run it. Run pro A pro B pro, and I got 0 and 42. Okay, so B passed to A 10 and 30. A responded with the sum. This sum was given here, and we got 42 as a result. If you now do the same thing on dependent types, so you make essentially this action dependent on the result, you can have a protocol where those steps are not fixed, but can depend on the answers. Okay. Okay, that's about protocols and some duality. Let's do carrying. So we case split on X, and we just pass both arguments around. What if this was a dependent function? So we'd like to have this product to be a dependent pair. So the implementation doesn't change, but this way we can carry a pair. Instead of a non-dependent pair, it's a pair. Okay, how much time do we have? 41. Okay, I'd like now to show the list type. And lists work similarly to Haskell, except you generally use double colon instead of a single colon. Okay. So we have a list. Let's write a single list. This works. Except if you try a list with 2 elements, it doesn't, because you need an infix declaration. So infix write something like this, and now we got a working list. Agda doesn't have a built-in sugar for list type. You can't say that this list is built-in and it will have some consequences, but it will not give you a syntactic sugar. This is a homogeneous list. Let's try writing a heterogeneous list. In this case, we will have an H list, and previously, after list, you were specifying just a single type, and now we will be specifying a list of types. So this will be a list of set to set. So what will be the nil case? So I'll show my first what we like to achieve. I'd like to have an H list of not bool nil, and next will be 10 true nil. So nil will be an ideas. H list of nil, except this nil now refers to this nil, right? Okay, and cons, well, we'll be getting some A and getting an H list of A's, and we're returning an H list of A colon AS, and now I need to bind that, so A will be a set and AS will be a list of set. Okay, so and this definition of X as compiles, so we can have a heterogeneous list. Let's write concatenation. First, concatenation of normal lists. Okay, so this is essentially the same thing that you see in Haskell. What about concatenation of heterogeneous lists? We have an H list of A, an H list of B, and we would like to obtain H list of concat AB, right? So our goal is H list of concat AB, while we have H list of B and H list of A. And we can write it the same way we write normal list concatenation. Okay, and that works. Notice how much Agda has to compute here to check that this definition is correct. It actually needs to partially evaluate this concat function to make sure that this concatenation works recursively. So here it is pretty smooth, but things like this can be pretty delicate to your definitions. So in Haskell, you might think that the interface of a file is just its type signatures, but in Agda, as you have seen with the magic example, often definitions make a difference whether you whether something type checks or not. And you can write two similar definitions, and it turns out that only one will type check, even though they are operationally the same function. Okay. Another way of thinking about HList is that it's a fold over product over a list. Right? So I have this list, and if I fold over product, it will be a product of NAT and a boolean and product of nil, which will be like the unit type.
But there is no dependency between the elements.
Right, you could have a list that was dependent this way. I didn't think about preparing it, but yeah, interesting question.
The element, the type of the second element might depend on the type of the first.
Yeah, that's interesting. I could think about this after the talk. Okay, another example is that I have this list NAT, and I can do this. Okay. Once I do this, I can define my lists like so. So you can have Haskell's like syntactic sugar for list type defined using a mixed fix operator. Okay, I think this will be it for today. Thanks everyone. Tomorrow, I think there will be more exercises than me showing things. So if you could, please prepare a laptop with Agda.